Okay, let's say if this one, this one actually is the written notes how you want to determine the uniqueness of the sufficient statistic. So we have y1 and also y2. Y1 is again is defined as a sufficient statistic. So we have sufficient statistic y1. And then we have the PDF there. Okay, PDF there, G1, Y1, theta. So let's say we have unbiased estimator y2. Again, the concept not a function of y1 alone, the concept of Rao-Blackwell theorem. So then there is at least one other function of y1 that is unbiased estimator of theta. Okay, we have expected value of y2 is equals to theta. And then we have at least one other function of y1. Again, it is also unbiased estimator of theta. Okay. So then our search for the best estimator, normally we restrict to the function of y1, which is we restricted on the function of sufficient statistic when we want to find the best estimator. Okay. Suppose that we have verified phi y1, phi y1, which is the another function of y1, we get expected value of phi y1 is equals to theta. Okay. So let's say you have another function, upside y1. Upside y1 be another function of the sufficient statistic where we have expected value of upside y1 is equals to is equals to theta. Because again, sufficient statistic is one-to-one function and it is not unique. So it can have several sufficient statistics. So that's why we have, let's say, phi y1 and then we have upside y1. But both are unbiased estimator of theta. So when we have both unbiased estimator of theta, we can write expected value of phi y1 minus upside y1 is equals to 0. So that means expected value of phi y1 is theta. Expected value of upside y1 is also theta. So theta minus theta, so you have 0. Okay, so if the family of G1, Y1 is complete, the function of phi y1 minus upside y1 is equal to 0 again, except on a set of points that has probability 0. So for every other unbiased estimator of upside y1, we will have this one lah. Phi y1 is equals to upside y1. So this determines the uniqueness. So thus phi y1 is the unique function of y1, which is unbiased estimator of theta. So that means if you want to find a unique function, okay, so first we will find sufficient statistic. And then we need to show that it is unbiased estimator of theta. Okay. The next one, if we have phi y1 has a smaller variance. Okay, if phi y1 has a smaller variance, then this statistic is unbiased minimum variance estimator of theta. So if we combine all these three properties, that means sufficient statistic, complete sufficient statistic, a complete family of your G1, Y1 theta, and then it also unbiased estimator. So it will give you phi y1, which has a smaller variance. So we will define statistic phi y1 as a unique unbiased minimum variance estimator. So ini yang part kedua, uniqueness tu. We define a uniqueness. Okay, so that means sufficient statistic. Okay, after sufficient statistic, we can also show that that sufficient statistic is unbiased estimator of theta. And then we will have to determine the family of your G1, Y1 is a complete family. Okay, and then it will derive you to have unique unbiased minimum variance estimator. Ataupun normally we will write as this one, that the unique, it is written as unique MVUE. So this one, unique minimum variance unbiased estimator. Okay. So in the question, normally we state that find the unique minimum variance unbiased estimator. Okay, so this relate to theorem Lehman and Schaeffer. So again, you have a random sample, and then we have Y1, sufficient statistic, and then the family is a complete family. Okay, so if there is a function of Y1 unbiased estimator of theta. And then this function of y1 is the unique minimum variance unbiased estimator of theta. So first, this one. Okay, first, sufficient statistic. Second, you need to show that the family is complete. Okay, the third one, you find unbiased estimator. So this will result as unique minimum variance unbiased estimator of theta. So this is according to Lemon and Schaeffer, the theorem of Lemon and Schaeffer. Yeah, so that's mean three properties lah. Sufficient, and then find atau determine the family is complete, and then the last one, you need to show that y1 is unbiased estimator. Then it will result to you unique minimum variance unbiased estimator. Okay, so this is related to example 2.10. So this one is geometric. So geometric distribution. So we have theta to the power x, 1 minus theta to the power 1 minus x. So x takes value 0 and 1. Sorry, geometric. Bernoulli distribution. Okay. Sebab kalau if we have geometric distribution, then normally your x start from 1 up to infinite. Okay. So this one you have Bernoulli distribution. You have 0 and 1 lah. Okay. So we want to show that y is equals to summation si is a complete sufficient statistic. So again, first we determine the sufficient statistic, and then we show that the family is complete, and then the last one, if you want to find uniqueness, so show that your y1 is unbiased estimator of theta. Okay, first we find sufficient statistic, so we use factorization theorem. Yeah, so we construct the joint PDF. So theta to the power summation si, 1 minus theta to the power n minus summation si. Yeah, so we have this one. Simplify. So we have theta over 1 minus theta to the power summation si, 1 minus theta to the power n. So by factorization theorem, y equals to summation si is a sufficient statistic. Okay. In this case, your hx is equals to 1. So this is your g, in this case, gy theta. Okay. So y is a sufficient statistic. So that complete the first one. You want to show that summation si is a sufficient statistic for theta. Okay, second, we want to verify that the family of PDF is a complete family. Okay, so again, since our y is summation xi, okay, summation xi, you have I equals to 1 up to n. So y now is a sum of independent Bernoulli random variables, so we will have binomial distribution. So this one you need to know lah. Okay, that means when we start with Bernoulli distribution, if we have y is equals to summation si, so your y will have a family of binomial distribution. Okay, so y is binomial NP. So again, if you want to show that this one is a complete, so find the expected value. So let's say we define gy. So you want to show that expected value of gy is equal to 0. Okay, so we construct the expected value. So we have summation gy and choose y, p to the power y, 1 minus p to the power n minus y. Okay, so split the equation. So you have p to the power y, 1 minus p to the power minus y. So which is does not depend on y. You factor it in front. Okay. Okay, so now we have p over 1 minus p. So to make it more simple, so we define another variable lah. So let's say you have your r. R is equals to p over 1 minus p. This one, r is equals to p 1 minus p. So we replace. So you have gy and choose y, r to the power y. Okay, so again, in here we still have the term gy and choose y, ry. Okay, we're not sure which one should be equals to 0. Okay, so now we have to define. Let's say we have hy, gy, and choose y. Okay, so to make it more simple, So it left us with hy ry. So since our r must be greater than 0, so r cannot be 0. So the only way to make sure your expected value is 0 is by setting the coefficient hy is equals to 0. Okay, so hy is equals to 0 for all y values. Okay, so for all y values, so you can write this one. That's mean for each probability hy equals to 0, you have the probability is equals to 1. Okay, so that's mean all coefficient are 0. So by this definition, y is a complete sufficient statistic. Okay, so that is how we want to show for a discrete distribution. The same thing as we show the first example tadi, Poisson distribution. Okay, Poisson distribution. So if we can use notation, you can use notation lah, or define another variable. Okay, let's say in this case we define R. R dengan condition dia your R must be greater than 0. Yeah. So then you have your hy. Hy is defined as gy and choose y. So the only way you want to make sure your expected value is 0 is by setting hy is equals to 0. So by the definition, y is a complete sufficient statistic. Okay, so that's mean the first one. Okay, the first one we already show. This one is a sufficient statistic. Ini sufficient statistic. So second, show that it is a complete family. So when you want to show that the family of PDF is a complete family, that's mean family of your sufficient statistic. So because we already derived your y equals to summation si. So that's why we have family of binomial distribution. And then you again play around how you want to prove that your expected value of gy is equals to 0. Okay. So that's mean the only way we define another function hy to make it more simple. So we set the coefficient is 0. So that's mean this family is a complete family and your y is a complete sufficient statistic for theta. So that's mean in your explanation, so please write lah, okay, write how you want to explain ataupun how you want to derive your proving. Okay, mesti tulis sikit ya, adalah explanation how you want to get this family is a complete sufficient statistic. Okay, so that is the first part. So second part, so now you want to show that this is a uniqueness. So uniqueness, that's mean you need to find unbiased estimator of theta. Find the unique minimum variant unbiased estimator of theta. So that's mean we have expected value of y. Again, y is your sufficient statistic, which is summation xi. So it can be written as this one. So each ex is theta because Bernoulli distribution. Okay. Each x1, x2 is theta, so all together you will have n theta. Okay, so to make sure that your y is unbiased estimator of theta, so that means the only way is by writing expected value of y over n. See, n tu is a constant. Okay, we use the properties for expected value, so expected value of y over n is equals to theta. So by using or by showing this one, your theta head, okay, theta head, y over n is a unique minimum variance unbiased estimator of theta. And then since your y is equals to summation si, so the same thing, theta summation si over n. So this one, x bar. So that means kalau let's say I set the question, prove x bar is the unique minimum variance unbiased estimator of theta. So it's the same thing. Okay. You get your y and then you show lah y over n. So y over n can also be written as summation si over n, which is give you n s bar. So that is your unique minimum variance unbiased estimator of theta.